So now we move on to an example of a two-sample test. And in order to do that, we're going to have to learn about one more distribution. So suppose that W1 has a chi-square distribution with degrees of freedom nu1, and W2 has a chi-square distribution with degrees of freedom nu2. And W1 and W2 are independent. Then we can look at the distribution of W1 over nu1 divided by W2 over nu2. And this actually has a distribution called the F distribution with degrees of freedom nu1 and nu2. Nu1 we refer to as the numerator, degrees of freedom, and nu2 we call the denominator, degrees of freedom. And this F distribution was developed by the geneticist R.A. Fisher. So we want to conduct a hypothesis test where we test the variation of one population versus another. So our null hypothesis is that sigma 1 squared is actually equal to sigma 2 squared. And our non-directional alternative would be sigma 1 squared is not equal to sigma 2 squared. We could consider alternatives like sigma 1 squared less than sigma 2 squared, or sigma 1 squared greater than sigma 2 squared. And these would be one-sided alternatives. So our test statistic is going to compare the variances of the two populations. So in order to do that, we're going to look at the ratio of the test statistics that we had previously. So we're going to define our test statistic F sub S, and we're going to take the ratio n minus 1 S1 squared over sigma 1 squared. We're going to divide that by n1 minus 1. And so you can think about this as being W1 over degrees of freedom. And then we're going to take n2 minus 1 times S2 squared divided by sigma 2 squared and divide that by n2 minus 1. And you can think about this as being W2 divided by degrees of freedom. So we can think about this as W1 over nu1, and then this one is going to be W2 over nu2. And so that has an F distribution. Now, of course, we can simplify this. We can cancel out the n1 minus 1 and the n2 minus 1. And when we do that, we're left with S1 squared over S2 squared times sigma 2 squared over sigma 1 squared when we do the division of those fractions. But the null hypothesis is going to assume that sigma 1 squared equals sigma 2 squared. So under the null hypothesis, sigma 1 squared is equal to sigma 2 squared, so those will cancel. And we're just left with the ratio of the sample variances, S1 squared over S2 squared. And the degrees of freedom for this test statistic is going to be the ordered pair n1 minus 1, n2 minus 1. So we're going to want to look at the rejection region for this test statistic. Okay, so we'll consider two different rejection regions. We will assume that S1 squared, the variance of the first population, is actually bigger than the variance of the second population. If not, we can just switch 1 and 2. We can just switch which one we call 1 and which one we call 2. And our rejection region is going to be the upper tail of the F distribution, where we have an area of alpha. And so for the one-sided alternative, we will do sigma 1 squared greater than sigma 2 squared. And the rejection region in that case is F greater than F sub alpha. And if we do the two-sided alternative, sigma 1 squared not equal to sigma 2 squared, we still end up in the upper tail of the distribution, but now in the upper tail where we have alpha over 2. And we will have the rejection region of F greater than F sub alpha over 2. So that's how that rejection regions are defined for the one-sided and the two-sided alternatives. So let's do one more example, and this example will be familiar from class. We will look at a survey that asked biostatistic students, again, how many hours of sleep they got the night before class. There were 24 students from a section of biostatistics that meets at 8 a.m. and 28 students from a section that met at 10 a.m. And the students in the 8 a.m. section got an average of 5.75 hours of sleep, a standard deviation of 1.2 hours, and the students in the 10 a.m. section got an average of 7.25 hours of sleep with a standard deviation of 1.33 hours. And is there sufficient evidence to justify claiming that a difference exists in the variability of sleep time for 8 a.m. students versus 10 a.m. students? Again, we will use a 5% significance level. So our null hypothesis is that the sigma for the 10 a.m. class, the variance, for the 10 a.m. class is equal to the variance for the 8 a.m. class. So I will label them as sub 10 and sub 8. Notice that I put sigma sub 10 squared first because the sample standard deviation for that was actually larger. Okay, and then the alternative in this case would be that sigma sub 10 squared is not equal to sigma sub 8 squared. Although the sample standard deviation for the 10 a.m. is larger, I had no reason to believe that the variance was going to be larger for one population versus another before conducting this experiment. Okay, so now what is our F statistic going to be? Okay, so it is going to be the variance for 10 a.m. squared divided by the variance for 10 a.m. divided by the variance for 8 a.m. The variance for 10 a.m. is 1.33 squared, and the variance for 8 a.m. is 1.2 squared. That comes out to an F statistic of 1.228. And our degrees of freedom for the numerator is going to be 27 because there were 28 students at 10 a.m. And then 23 because there were 24 students at 8 a.m. Okay, so what we want to do is we want to find both the p-value, so we want to figure out the p-value, and we also want to figure out what we should compare F to. So what is F for 0.025 with degrees of freedom 27 and 23? We want to figure out what that is, and we also want to figure out some sort of bound on the p-value. So what we're going to have to do is look at the F distribution chart. So we have not looked at this one before. This is the F distribution chart. Notice that the probabilities are in the upper tail of the F distribution. And notice that going across the top are the numerator degrees of freedom, and going down the column are the denominator degrees of freedom. So what we'll have to do is we'll have to cycle through this chart until we find a denominator degrees of freedom that works for us. So I'm going to keep cycling through this chart until we get a denominator degrees of freedom of, denominator degrees of freedom of 23. So now I've finally seen 23, but numerator degrees of freedom at that point only goes till 9. So I'll keep cycling through this chart until we get a denominator degrees of freedom of 23. And a numerator degrees of freedom of 27. It seems to be right between 24 and 30. So the F statistic for F statistic for 0.025 is right here in this row, and we're going to come across, and it's somewhere between 2.3 and 2.24. So I'll be conservative and I'll use 2.3. Now, our F statistic, the one that we calculated, actually was 1.228. And so I'd have to look on this chart and see where that would be found. I noticed that alpha is 0.1 here. So 1.228 would be somewhere here above that. So that would be above an alpha over 2 of 0.1. So what I'm going to do is I'm going to remind myself that was a alpha over 2 of 0.1 for 1.228. And then I had a 2.3 for my F statistic. So coming back to this example, my F statistic was about 2.3, and P over 2 we said had to be greater than 0.1, so that meant that P was bigger than 0.2. So we can say that since F sub S is, in this case, our F statistic is less than the F statistic for 0.025 degrees of freedom 27 and 23, okay, or P is greater than 0.2, okay, we cannot reject the null hypothesis. So what can we say then? There is not enough evidence to conclude a difference in the variances.